All right, welcome. Happy Friday. Big turnout today. No, that's okay. Let's get started. So last day, we finished chapter 6, which was kind of a quick run through of inference. And just like chapter 6, chapter 7 is also going to be review if you've taken a stats course before, or if you're taking Stat 230 with me. We're going to get there. So I'm going to, try to do my best to kind of cover all the bases. And the theory material on the quizzes will just be what we talk about in class, right? So it's not going to be too involved beyond that. So I just before class, at first I thought I would post just, the first half of chapter 7, the summary notes, because I didn't think I'd finish. And then I'm so stubborn that I managed to finish them, but it was like just before class started. So I just posted them. And it's a summary of linear regression, although it's just regression, because we do talk about nonlinear regression as well. So it's going to be a review for many of you, and a quick introduction to regression for the rest of you. Okay, so kind of tough, but that's okay. So just in general, okay, so chapter 7 talks about, is called linear regression. And regression is when we use sample data to build a model, right? A regression model. And the goal is to be able to predict future values. Okay. And so we build a model. We build a model to try to predict future values. Future values, not in the sense that they're necessarily in the future time-wise, but kind of different values that we haven't seen in our sample yet, right? That could happen. Notice that here we're transitioning from descriptive statistics, right? And now we're making predictions, right? So remember that the multiple layers of analyses, we said, okay, well, we could do descriptive statistics, just, basic inference, like, is the mean different from this value or not, right? And so we can describe what's happening in our data, right? And then we can infer something about the population. And now we're introducing this new level where we're able to make predictions, right? And so we started with descriptive analyses, and now we're moving towards predictive analyses. And then the last step, which we're not going to get to because it's kind of beyond the scope, but it is in the textbook, is prescriptive, right? So if you've made a prediction, what is your prescribed path to take after that, right? And so what's your prescribed kind of decision, right? And so recall the 3 types of analyses. Oops. Introduced in chapter 1. So the first one is descriptive. Those are things like summary statistics, basic inference. Summary statistics, right? Graphs. Basic inference. I would argue all inference, but I'm going to stick to basic inference. right? So those are all under the descriptive umbrella. Now we're moving on to predictive, which is going to be regression. We'll stick to regression for now. We're going to see some more, right? But for now, this is all we're seeing. And so now, right here, we're kind of kicking it up a notch here. And we're saying, okay, we're going to be able to predict future values. Okay. And then finally was prescriptive, and I can never remember how to spell it. Prescriptive. Okay. Oh, got adjusted here. And so that's when we use predictions to prescribe some decision. Use predictions to prescribe, I don't know, a decision, right? If you predict that you are going to, I don't know, sell less than $1,000 worth of whatever, then maybe you shouldn't be doing it at all, right? Or maybe you should increase the number of man hours, right? So now you're attaching some decision to the prescription. So of course, to the prediction. But first we need to know how to predict stuff, okay? And so one of the main ways that we do that is we build a model, and that's called a regression model, and we're trying to predict future values, okay? So you might remember that in general, we have some dependent variable. You could also call it the response variable if you want. And it would go on the y-axis, and on the x-axis, you've got your independent variable, or the explanatory variable is what I like to call it, because it emphasizes that the x-axis has the explanatory variable, right? But in general, we're going to build some model. Okay, so imagine you've got your data here, and maybe I'll make my pen a little bit bigger so I can make some dots here. Maybe like that, right? So we've got some XY combinations, and I'm trying to build a model to try to take some value of X and predict the value of the Y that would happen, okay? And so regression, oops, change my pen back. Regression, and maybe, no worries. Everyone is running behind today. Thank goodness for the weekend, right? So no problem at all. So regression, right, is trying to build a model, tries to model this relationship between X and Y. Regression models the relationship between X and Y. In simple linear regression, we have a straight line. So a linear relationship means that we just have a straight line. And the simple is referring to that we just have one explanatory variable, whereas later we're going to talk about multiple regression, and then we're allowing for more than one explanatory variable. But one caution is that we don't have this 2D graph anymore. Now we're going to have essentially the y-axis here, and then you have this kind of 3D graph, and anything beyond that is really impossible for us to imagine, right? And so we can still do it, but we can't really visualize it. So for visualizing, we just think about two variables, x and y, and I've got a graph that shows you what it would look like for two explanatory variables, but we'll leave that for a little bit. So regression models, regression models, the relationship between x and y. Wow. And so simple linear regression has one explanatory variable, that's what the simple comes from, and is best modeled by a straight line. Oops, can't write it all today. Right, and that's where the linear comes from. So if we go here and we look at this relationship now, I just drew these dots, right? So you would look at your scatter plot and we would draw a line here, and we would just imagine, how could I model this relationship? How could I summarize this relationship between x and y? And so we might build a line that looks something like this, right? And so for the population, what we're going to have is and maybe I should go back to the notes here. Let's see here. It's all slow. Maybe I'm too fast. So here, right, for the population, what we're going to have is this nasty looking model, but once we pick it apart, it's not going to be that bad, right? And so if you remember, and if you haven't done any regression before, then you might have to go back into the memory files, but you might remember that a straight line, a straight line has equation, generally we like to use y equals mx plus b. I'm not sure why we do that, but we do. Y equals mx plus b, okay? Where m, of course, is the slope because it's attached to the x, and b is the y-intercept. So if we map that knowledge to this here, because it looks like we've got a similar situation, right? But for the population, we have this beta naught. Now beta is for the population, it's a Greek letter, right? So it's from the population. And so here, this is the population y-intercept. Beta 1 is the population slope. And epsilon is the error term. Yeah. Because there will always be some variation, as we saw here, right? There's going to be some activity around the straight line that we can't capture just by the straight line. We're going to try to build a line that captures most of that activity, but we can never capture all of it. So we have to allow that error term. So in terms of our sample data, right? So now we have our population model, but really what we're going to have is we're going to build a model, and that's our estimated linear regression equation. Let's see here, come on. So here we have y hat is b naught, right? Any subscript 0, we usually read it as naught. So b naught plus b1x. Now this is going to be the regression equation for our sample, right? So it's the estimated simple linear regression equation. So that means it's from the sample. Just like the sample mean is our best estimate of the population mean, the estimated simple linear regression equation is the best guess at the population linear regression equation, right? Same idea. So now I have this sample y-intercept. Oops. And I have a sample slope. One thing that might look new is this y hat. Now y hat is different from p hat. You might remember I like to use p hats for the sample proportion, but that hat is different from this y hat because in context. And so y hat, we use it to denote the predicted value of y. Now that only applies in a regression situation, right? So y hat is the predicted value of y. And so this is different from p hat, which is the sample proportion. This is different from p hat, which is the sample proportion. Okay, so that's just something to keep in mind. Now this textbook, right, uses p bar, and I think it's to avoid that, but then we have this kind of crossed wires with x bar and p bar, but doesn't matter. So in terms of this line that we drew on here, this line is built off of sample data. So we can't use the population equation, but we can say that y hat is b naught plus b1x. Okay, and so that's the model that we're going to try to build. Depending on the slope and the relationship of the data, okay, we could have a positive linear relationship. Now notice it always has to be linear, otherwise we can't model it with a straight line. I'm going to introduce just briefly some other non-linear relationships that you could look at, and often they cover all your bases. What this textbook hasn't talked about yet, or doesn't talk about in chapter 7, is that we can make transformations on some of the variables to make a linear regression. So even if you don't have a linear regression, you can usually force a linear regression, and that's kind of cool because a linear regression is really kind of easy to do and almost fun, some might say. So if we have a positive relationship, it means that we have some relationship that looks like this. So it's going up. So as x is increasing, y is also increasing, right? If you have a negative relationship, then the slope is going to be negative. Hopefully that rings a bell, right? And as x is increasing, y is decreasing. So that makes a negative relationship. The third relationship, I'll put relationship in air quotes because it means there's no relationship. The third option is if you have a slope of 0, right? And so what that would look like is if you had something like just random scatter here. I don't want to put it all over the, the text, right? Whereas if you have a relationship that looks kind of like this, or like this, trying to just not block out any text too much. Okay, so it should be fairly obvious which direction your data is going. So if you just have this cloud, you can think about, well, it doesn't really matter. I could put a steep slope like this, or a steep negative slope, and it doesn't really matter in terms of describing what's going on in there, because you're just hovering in a cloud. And so then the slope would become essentially 0. Okay. I'm pretty sure it's in the text that I posted there, but the intercept, oh, wait, keep forgetting to change my pen back. The intercept is the predicted value of y, right? And so maybe I'll jot down what the equation looks like, right? Y hat is b0 plus b1x. So the intercept, which is b0, is going to be, by definition, the predicted value of y when x is 0, right? So just pretend that x is 0. And where is that? That's on the y-axis, right? And so that is the y-intercept. And so by definition, the intercept is the predicted value of y when x is 0. Okay. The intercept, or the y-intercept, is the predicted value of y when x is 0. Okay. This is really only useful information if x can be 0. Okay, so this is only useful for interpretation. It's useful in the sense that it anchors our line, right? So this is only useful besides anchoring our line. Besides anchoring our line. So this is only useful if x can reasonably be 0. If x can reasonably be 0. Okay. If x can't be 0, if that's illogical, then you shouldn't really be interpreting the intercept as the predicted value of y when x is 0 if x can't be 0, right? That is the definition, but it's not really useful information that you incorporate, right? Whereas the slope is always important. So the slope, which is your b1 in this case, okay, the slope says that for each, so by definition, for each unit increase in x, right? So if I increase x by 1 unit and the y-intercept stays the same, then if I go from x equals 0 to x equals 1, for example, then I see a slope increase in the predicted value of y. Okay. And so for each unit increase in x, we expect to see a slope increase. And you have to be careful here. You might see a negative slope, right? But if you say a -4 increase, that's correct, right? But you don't want to say a -4 decrease or something crazy like that. So I usually just use the word increase. So for each unit increase in x, we expect to see a slope increase in the predicted value of y. Yeah. So those are just the definitions, and I think those are going to serve us well if we have those kind of in mind as we're looking at some of the output. Now, in this course, we are just going to use software to find the formulas, right? So we're not really going to talk, I'm going to talk a little bit about, how did we get these formulas? And then in Stat 230, if you haven't taken it, then we'll talk about, what formulas can we do? How can I find the value for the slope? How can I find the value for the intercept without necessarily using software? Whereas here, we're just going to assume that we are going to use R, and I'm going to show you how, not today, but I will show you how to build a regression model once we've introduced all of them, right? Because then we can do a couple of different examples. Or a couple of different models, I should say. So in terms of how are we going to find this model, and by we, I mean R, how is R going to find the model that we're looking for? I guess I have to put it on a fresh page here. It's okay. This is all kind of mumbo jumbo, but unless you like reading summations, maybe you do, maybe you don't. But the method that we're using is called the least squares method, right? So you might have heard of least squares regression lines, that kind of thing. And that's the method that we're using is the least squares method. Now, there are other methods, but this one is the most commonly used. Okay, so I will say that here. There are other methods, but this is the one that's most widely used. But least squares is the most widely used. Okay. So the least squares equation, what it does is it minimizes the sums of the differences between the observed y from the predicted value of y, and then we square them. So the least squares, the least comes from the minimum, and the squares comes from the squared values. Okay, and so we could rewrite that if we wanted to, but usually I just talk about this one here. So we have some observed value, yi. Usually we just use a little subscript I to denote the observation, because now each observation is going to have some x and a y coordinate, right? If we're trying to plot them on a graph, right? So I'm going to have some observed value of y, and then I'm going to have some predicted value of y based off of my hypothesized line. Now, what gets kind of confusing and mind-boggling even for me is, okay, so I need to have a line, because the predicted line is this line that I've drawn, right? And so I need to have a line to find the line, right? So the way we find these is a little bit tricky, and so we let software do it. We can do it, but the idea is we need to find the line that minimizes the distance from each of the points squared. Okay, and squaring that distance, what it does is it does two things, right? Squaring a value makes it positive, but also a distance of 1 squared would stay 1, whereas if I double that distance to 2, then 2 squared becomes a squared difference of 4, because a distance that's twice as large is more than twice as bad. Okay, so you have to try to accommodate that. And so here, let's write a little note here. Let's see here. We minimize the distances between each observation or each observed y and its predicted y, which is your y hat, right? Predicted y is your y hat. So we minimize that distance by taking the difference and squaring it. Okay, we use the least squares, so squaring it for, like I said, 2 reasons. So we use the least squares method. And so I'll underline that it's for the squares that I'm talking about. So we use the least squares method for 2 main reasons. Okay. First one is squaring a negative value gives you a positive, right? Because otherwise you're adding positive values, so values that are above the line and values that are below the line. If you just sum those, you're just going to end up at something close to 0 all the time, right? Those negative distances, which we're going to call residuals or errors, right? Because they're error from the line. But for now, we can just call them distances, right? Yeah, if you add them up, they just, the negative values cancel out the positive values. I don't know why I got hung up there, but I did. So we use the least squares method for 2 main reasons. Squaring negative values yields positive values. So that the sum of the differences squared, or so that the sum, and I'll put the sum of the yi minus y hat squared, right? That's the sum that I'm talking about. And if you want to, if you don't like looking at the subscript I, you don't have to have it there, but just remember that we're talking about each individual observation, right? And then we're adding those all up, all those distances. So, so the sum of these will be positive and not 0 all the time. Right, that's a problem. And so squaring them, another thing you could do, and there is a method for it, you could use the absolute values instead. But the second reason is why we don't do that. Okay, so squaring a distance that's twice as large is going to highlight that a distance that's twice as large is more than twice as bad. A distance twice as large is more than twice as bad. Okay, so in terms of trying to make adjustments there, so if you have a graph that looks like this, and let's draw your least squares regression line here, y hat is b naught plus b1x. And then maybe I have, let's draw some points here. Okay. So here, oh, I should just have it on the graph there. So this distance from here to here if the predicted value of y here is, let's say 4, and the observed value of y, here's the predicted value of y, so y hat maybe is 6, and yi equals 4, okay. That distance is yi minus y hat. So now you're going to get this negative distance. And I'll use orange here instead. Yi minus y hat, oops. Is called the residual or the error term. So basically what we're trying to do, right, we are going to square each of those distances, okay, but essentially what we're trying to do is we're trying to find the line that makes this all these distances as small as possible, right, and that's going to be our line of best fit. Okay, so that's what the least squares regression line does. Try and get it to catch up here. Oh, I already had it. Oh, okay, that's okay. I'll just scroll up. So it gets a little bit confusing, right? Because we build a line, but basically using software, what we can do is we can, in theory, we could run all the different possible lines, and then we pick the one that minimizes those distances. Of course, we could use calculus and we could try to minimize those distances, right? Optimization, we have to use calculus, and so we don't want to go there, but that's what's going on in the background. But what it all hinges on is this error term. So the error term here, it's written as E subscript I, and we can call it the residual, the ith residual. Why isn't it called R? Well, probably because correlation is denoted by R, right? And so we had to figure out, okay, E works for error term, but error term, like we said, is just yi, so each observed value of y minus the predicted value of y. Okay, and so what we understand is that all our points aren't going to be exactly on the line, so there will be some error terms, right? And they're exactly what you think they are. Okay, and so we could talk about minimizing the sum of the error terms squared, right? That's the exact same formula as here. It's just a little bit easier to read, at least, right? So we say that we're estimating the regression equation that minimizes the sum of the squared errors, and that's the method that we're using. Okay. And maybe I'll follow it up with here, E subscript I, right, for the ith term. Okay. Wait, can't do that. So usually we use software such as Excel or R, right? And so I'm going to show you later, once we've introduced a couple of different models, I'm going to show you how we find B1 and B0, but we can do it given some sample information. We can do it by hand, but we're not going to do that. So one thing that's really important to remember is that we've got our sample information, right? And so we've got some scatter plot, and our X values only run over some experimental region, okay? And so our model only really applies to that experimental region, okay? So I'll highlight that here. So you can use the regression line that you built from that sample. You can use it to predict future values, but just like we said with the y-intercept, we don't want to do that unless it makes sense, right? And so we can't do it because we don't know that our sample or our population is going to look the same outside of the range of the x's that we've looked at. Right. And so when we're trying to predict values outside the range of our x's, that's called extrapolation. Okay. And so prediction of the value of the dependent variable, so that's your y, outside the experimental region is called extrapolation and is risky. Right. And the reason for that is because your results are not as reliable as they are based off of your sample information. Okay, so you can make predictions outside of the interval, right? Outside of your x values, but you don't want to do it if you don't have to. Okay. We can use the model to make predictions for any value. Oh, time flies. To make predictions for any value of x. But we should try to restrict it to the values of x that are in our sample, right? But we should try to restrict it or restrict our predictions to values of x kind of within the range of our x values in our sample. Within the range of the x values in our sample. Oh. Man, it's slow. Chop that off. There. So what we could have is we will have some sample information, right? Some X, Y coordinates. And then what we're going to do is we're going to build this line. Now, in this case, I kind of skipped into an example, but of course they talk about it in detail in the textbook. But we're talking about how does the travel time depend on the number of miles traveled by some trucking company, right, with different drivers, different driving assignments, right? So here we have a sample size of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different driving assignments, right? And so we're able to look at how many miles did they drive and how long did they drive in hours, right? And then we're trying to predict the travel time based off of how many miles they have to travel, right? And so we have this sample of size 10, but of course now based off of this sample, we can extend these results and make predictions for maybe if someone's going 60 miles, right? Then this value of y of roughly 5.5 would be our best guess at how long it's going to take them, right? And so just as a couple of facts here, so the sum of the predicted values is going to be the sum of the values of the dependent variable of y. And that's just kind of an interesting fact. We're not going to use it so much, but it's true. Another kind of fun fact is the sum of the residuals is always 0, right? And so the reason for that is because we're trying to minimize the residuals, and it just happens that that's going to make a sum of 0. So that's interesting. Notice that we're not squaring these residuals anymore. And then, of course, the sum of the squared residuals has been minimized. So these are just fun facts. Or little fun facts, maybe. LFFs, little fun facts. So what we're going to see is, okay, our line is doing a good job of modeling this behavior here, right? This overall trend, but we also see that if the line is representing the predicted values, then for some of these, right, these values, all the values below the line, it over predicts how long it's going to take. And for the values above the line, it under predicts how long it's going to take, right? So here, the line is the predicted value at each value of x. And then, because I'm out of time, I'll just rely on this little note here. The regression model under predicts travel time for some driving assignments, right? And over predicts the travel time when the residual is greater or less than 0, right? So a little bit confusing, but you can look at it and say, okay, well, for these values below the line, these are over predicted because the line is over the, so the line is the predicted values and it is over the observed. And these guys are all under predicted. So you'd have to take some time to wrap your head around that in each scenario. But blink and you miss it for our Friday classes. So I'll end it there, but have a look through the rest of the summary notes. And we'll keep going through chapter 7 on Monday. If you have any questions, let me know. Otherwise, have a great weekend, and I'll see you Monday.